Let me start the recording here because I don't have G in right now. But I'm going to start with number 5 because I think I went up to number 4 before I ran out of time last time. So what we want to do is we want to make sure that we understand how to take a problem that is now not explicitly a power function. Yes? I got 3? Okay. So we can call this 4. It'll be fine. I appreciate that. I'll just be off of my notes just a tiny little bit. So is this, now by the way, I have to be a little bit clear here. This is not a power function, nor will it ever be a power function, because a power function only has one term. This one thing, after I manipulate it, would be 3 independent power functions. So I want to be really, really clear. But what I want is each piece to be its own power function. But because I have a monomial denominator, and please hear that well. You see mono, there's one piece. Because it's a monomial denominator, I could break g of x into 3 pieces. What would be that first piece? If I decided to divide everything by that x.
Hey, Penner, will you share your screen, please?
Yeah, absolutely. Let me go ahead and try that one more time.
Thank you.
Thought it would have been there, but it wasn't. So let's just say that we divided everything by x. So I'd get 3x to the 4th, wouldn't I? What would be next? Negative 2x. And this is a little bit strange. You're not going to like this because now when I get to that last spot, I have 1 divided by x, but that's not how a power function looks. Remember, a power function is supposed to look like that. It's supposed to look like ax to the k. So how would I take 1 and divide it by x and make it look like ax to the k? X to the negative 1. So I have plus x to the negative 1. So I'd be calling a 1, and I'd be calling k negative 1. Again, to be clear, this is not one power function. It's actually 3 independent power functions. And the rule that we had yesterday is that if you have some function that looks like this, what was h prime? Let's see if we could recall from yesterday the trick, the magic bullet that makes us save truckloads of time. A times k, x to the k minus 1. And so this takes a problem that I kid you not would probably take me 20 minutes to solve because of all of the distributive property. I have a fraction in here, so I'd have to do a fraction buster and distributive property. Holy smokes, and all of this would be on top of this massive fraction. Makes you cry to think about it. And then we could just look at it and say, oh, no big deal. G prime of x is, what's my first step? This is so silly how fast this is. 12x to the 3rd. What's the next piece? Now that's, you gotta be really careful. Why is it just plain old minus 2? Because 1 times that, also negative 2x is a line whose slope is negative 2. And remember, a derivative is just what's the slope. And how about this? Ooh, be careful. That'd be negative x to the minus 2, right? Now, it is pretty typical for us to not like to write things in that form, I will say. Normally, we don't like to leave things with negative exponents. So the majority of times, you would have people write it in that format. But a problem that should have taken a tremendous amount of time didn't take any time at all, did it? You guys like that? You see how when my brother taught me how to do that trick, then when my teacher told me to do it the long way, I almost couldn't make myself do it. You know, it's like going to the dentist and getting your teeth drilled. It's like, I'm okay. It doesn't really hurt. I'm going to be all right. Just don't drill my teeth. I don't want to deal with all that stuff. So I kind of messed up, and my teacher fried me for it. I do want you guys to know how to do that. I just didn't realize why it was that important. But anyway, I'm not going to make you guys sweat through that for as long as Mr. Newell made me sweat through it. Okay, but it's all good. All right, moving on to example 5. I don't have very many examples, to be honest. They were almost done with what I wanted to do. Definitely not a power function, nor is it currently a couple of power functions. So, but I have a monomial denominator, so I can get away with this. What are we going to do? What happens when you divide these two? Ooh. That's 2x to the 3/2. Very good. Because what do you do with the powers? You subtract them. And this one was a 2 power, this was a 1/2 power, and 2 take away a 1/2 is 3/2. Oh, and then what would this other one be? 5 divided by that would be 5x to the negative 1/2. Now, why was it negative? Because it was a square root and it was in the denominator, so we had to do that. So now, how do I denote that I wanted to take the answer to the derivative here? I write j prime. We write a little tick mark right there. Be really cautious that you don't get too lazy with those tick marks because they mean something pretty significant. So if you're lazy and you start writing them well and somebody misses them, it means something. So product rule, what would that be? 3x to the 1/2. I like it. And then what? Why'd you get a positive? Oh, it's a negative times a negative. And what happened to that exponent? Negative 3/2, because we have to religiously make sure we're always going down 1 unit. So again, is this a good answer? Yes. But sometimes somebody might write that in a slightly different format. I think everybody kind of knows that. But the slightly different format, instead of writing 3x to the 1/2, what could we say? 3 root x plus 5/2. And be careful about this. How do I write x to the minus 3/2? That would be the square root of x cubed. Again, that might feel a little awkward. The square root comes from the fact that it was anything divided by 2 is a square root. If it was divided by 3, it would be a cube root, etc. And we go through it that way. Now, just so you know, as we proceed through all of this, there is certain notational little idiosyncrasies that we have. So see J prime? J prime is the answer to the derivative, right? That's not an operator. I've made reference to the idea of an operator before. A sign is an operator. You just don't write sign, you write sign of something, right? A square root is an operator. It's the square root of something. What else is an operator? Addition. Is addition an operator? You don't just write plus on the board. You don't write 6 plus and just like leave it hanging. It has 6 plus what? So as it turns out, this is not an operator, but sometimes like you want to do that. You want to say, hey, here's my direction. Please go find the derivative. And so what happens is this is a slightly different version of that. But if you ever say d dx, that is the direction to go ahead and do something. Now again, just like before, on purpose, I did not give you a power function. I gave you the product of 2 power functions, or at least related to power functions, right? And what is this d dx saying? Hey, go find that derivative. Can you please find the derivative? It's the derivative of what's, see how it's operating on this? So what would the answer of all of this stuff be? That would be the derivative, okay? So oftentimes, what would we call things in a math class is we would call it, say, y, right? Don't we a lot of times say y equals blah, blah, blah? So there's a couple of ways that we could do this. I'm going to write this down here, and then we'll fill it in. Sometimes we call it f prime, and other times we call it dy dx. That's kind of new. So do you see the d dx? That d dx is the operator. Who did it operate on? On y, on that whole thing. So f prime of x and dy dx are not operators. They're just like the actual ultimate answer. But d dx means let's take the derivative, and the variable that's going to change is x. What would d dt be? The derivative of, or t becomes the variable. DDA would be take the derivative where A is the variable, and you can kind of do all of that. But see, there's a problem here. I don't know how to take that derivative yet. I have a special way that we're going to learn soon, next week, called product rule. How could I turn that into a power function so I actually can apply the rule that we know? Can I multiply it out? Oh, that wouldn't be too bad. So let's see, what happens if I start multiplying it out? What's the first term you guys see? I see x to the fifth. I see 2x to the fourths. What else do you guys see? So I'm distributing. I think there should be an x squared coming from here. And what's the last piece? 5x. And so what is ddx of x to the fifth plus 2x to the fourth plus x squared plus 5? Instead of a 20-minute long arduous question with lots of limits and canceling and all sorts of things, we can write the answer. What is it? 5x to the fourth, 8x to the third, 2 x's, and a 5. Don't you guys like the power rule? Isn't that such a friendly little thing? So nice. Now, for obvious reasons, we're not going to spend a whole truckload of time in that home because, well, let's face it, there's, yeah. Oh, did I mess up? Oh, that is funny. Thank you for catching that. I got x to the fifth. There should have been a 5x to the fourth. Thank you for that. I was looking back at my notes and I think I copied something over wrong. So 5x to the fourth. Let me double check and make sure I don't have any other dumb mistakes. And I missed the 5x here, didn't I? Okay, now I'm feeling better. So this should have been what number? Oh yeah, they're 20. And I think I fixed everything else as I went. I just didn't write it down correctly. So, okay, good. Now, I want to go ahead and flip over and do something that is a little bit tougher. And what I'm trying to do is make sure that even though today is a short day, it actually makes a little leverage towards something that's pretty hard for next week. And I think you're going to kind of understand the complexity of this, but it's a tricky little equation problem. So in my next one, which is, I guess I could call it number 7, but it's not really directly related to those other problems. But here's what I've got, is I've got some function f of x is x squared plus 8x plus 6. Now, of course, x squared plus 8x plus 6 is just some simple parabola, right? Now, I don't really need to graph it, but if I did, it would have opposite b over 2a. It would be like out here at x equals -4. It's going to be some graph that kind of goes like this. And I will actually eventually pull that up on Desmos for us so we could actually take a look at it. And I've got this coordinate over here, which is the coordinate 1, 6, which is actually right here. Probably my scaling is kind of poor. And what I want to do is I want to find the equation Oh, don't you hate it when a teacher puts that little parentheses S on the end? What am I telling you? They could be 1. Dang. Which one is it? I have no idea. Shoot, we're going to have to figure that out. Let's find the equation or possibly equations that pass through one comma 6, but are tangent to the curve. And yes, I put exclamations because I think it's pretty cool. So, how in the heck could I do this? Well, I think you might kind of appreciate the fact that if I kind of put my ruler right here, if it's going to be tangent to the curve, you guys, what's supposed to happen? It's supposed to hit the thing, and it's supposed to just barely touch the curve, maybe right down there like that. Let me go ahead and do a quick stop share. Oh, there he is, actually. Reese is coming in. But it's supposed to look something like that. So what are the, I did lay this foundationally out last time a little teeny bit. So if something is going to be tangent to a curve, what has to happen? What's first that must be true? It has to touch, doesn't it? Okay. So our little rules is a tangent, number one, must intersect in how many places? One place. In one point. Number two, what also made it work? See, because if I went like this, it did cross the curve right here in one point. What did it also have to have? Because we saw this yesterday. It had to have the same slope. Two, it must have the same slope. Let's go ahead. Oh, did he enter after all? Let me double check that thing, see if Reese is back in. I think he is. All right. So this is kind of interesting. So what actually happens here is that's actually very, very helpful because see each of these two things right here? That actually creates, for me, not just one thing, it creates two things. So here's what I know. I have an equation of a line, and you guys know that I love this form of a line, right? I think I've probably landed that plane a few times, right? But that's a good form of a line. So what would you guys know about this silly thing? I have my point already, don't I? I know that my point is the point 1 comma 6. What do I not yet know? Oh, but I do. I do. You're not going to like it, but I do know the slope. I do know the slope. Do I know the slope of the curve? Because I know the power rule. You guys see that? So I made it have the right point. I made sure that I had this. Now I'm going to go ahead and distribute that out a little bit because this is kind of weird. So just, believe me on this one so we could spend a little bit less time here. But if you were to distribute that out, kind of clean it up a little bit, this is what would happen if you took the time to distribute as well as move that 6 across. Yeah, I think I did that right. Something feels a little bit hinky about it though. No, something's wrong here. So maybe I shouldn't have done that fast. I got 2x squared for sure. I got a negative 2x and a positive, which is 6. Right here, I got a negative 16, right? And when I add that 6, it's negative 10. My notes are jacked. Okay, because I was going off of my notes, so I would save some time, yeah. Oh, that's where I went wrong. Thank you. And now I was right, because I knew my answer that I had in my stuff was actually going to work. There's a -8, and I moved that 6 across. It is a -2. Whew, I was right. I just copied the point wrong. So I took the 0.16. Let's just reiterate. I took the 0.16. Everybody understand where I got my slope from? But see, if you go over to here, I now have the same slope. This is really important. I have the same slope. What do I not have? If you look over here, is I never made them intersect. So I've got this new equation that was y was 2x squared plus 6x minus 2, but my original y was x squared plus 8x plus 6. See, I got the same slope up here, and I'm making them intersect down here. I'm making this brand new idea intersect the original problem. Now, this problem was 100% rigged. If I made up like 1,000 problems at random, trust me, none of them would give me nice answers like this. I designed this to be really, really kind. So if I move some stuff around, keep moving things around, magic happens. It's really difficult to make a problem come out perfect, especially this far in advance. You know, because I actually rigged all of this and sat down and I kept moving that point around until I got really nice values. This factors. Factoring is still a great thing, isn't it? So what does that make x? 4. What else does it make x? Ooh. Now wait a minute. I didn't really answer the question. It didn't say find the place where it happened. It said find the equation of those tangent lines, didn't it? So let's go right up to here. Oh, here's my line. It was y minus 6 is equal to something times x minus 1, wasn't it? But I know that x, because keep in mind, this part was my slope, wasn't it? What happens if I plug 4 in right here? I got 16. What happens if I plug in -2 into that little hole? Now, that's a little surprising when you look at it through that lens, that there's actually not just one answer, there are actually 2 answers. So let's take a look at how that actually plays out. I'm going to go ahead and take a look at this thing. Let's do a new share. So we had a nice little equation, which was x squared. I knew it was going to drop. X squared plus 8x plus 6, right? Simple little equation. I had some point over here, which was the coordinate 1, 6. By the way, can you guys do this yourself when you're doing your homework? And we just came to believe that if I type the equation y minus 6 equals 4, now where did the 4 come from? The 4, I plugged it back in to find the slope at that x value, and that was x minus 1, because we're going to be a little bit more careful to make sure that we actually hit the point and not something off to the side. What just happened? Did it hit perfectly down here, and how did it hit? In exactly one point, right? And what would be true of the slope of both the line and the curve at that point? They would have exactly a perfect slope of 4. Well, the other one is kind of weird. It's very difficult to see because when I do this one, the other slope was what? How steep is 16? It's stupid steep. I mean, it's up here like this. So like if I zoomed in and like, whoa, where'd it go? See, I'm finding out. It's up here somewhere. Now, would I be able to find it? Yeah, I could find it because it happened when x was, I believe, the number 4, wasn't it? So if I went back to that original function and I found out, let me do that real quick, f of x. So if I change that to f of x and I asked my calculator, hey, what is f of 4? Oh, it's 4 comma 54? Oh, so the coordinate 4 comma 54, that's the place where they should be crossing. Let me label it so I can see it. Oh, that's where they cross. Well, not very informative though, was it? Because the graph is so dang steep up here, you really can't see the difference between the two of them. So that's a pretty hard problem, wasn't it? There was a lot of steps in that. But as you go through all of that, hopefully you guys caught what was going down, that as you went through it, we had to ensure two things. Number one, that they have the same slope, and number two, that they actually crossed each other. So I thought it might be nice to do one more problem kind of that nature. And so your problem right here is going to be, let's do a very simple one, y equals x squared minus x plus 3. And I'm going to go ahead, and this one may not come out quite so nicely. I wish I had set this up a little bit better. Actually, yeah, I'm going to cherry pick something off of my work right over here. I'm going to pick a different equation because I think you're going to like it better. We're going to pick the equation x squared minus 2x plus 1. And I'm going to pick the coordinate 5, 7. And let's see if we can come up with the two equations that would do that. Again, we've got some kind of a parabola. We've got some rando point over here. It should be like the previous one where we end up with two places where they could actually cross, but let's see if we can follow our process. I made a little note. That's supposed to be my tangent line, isn't it? So here's my line. Do you guys see that? Y minus y1 equals m times x minus x1. Isn't that a line? That's kind of weird. That's supposed to be my tangent line, right? Why does it not look like a line? Because I don't know what x is yet. And as soon as I know what x is, then I could say what that line is. What do I want to set that equal to? The original, yeah. Not only must they have the same slope, which I did, I need to now make sure that they actually cross. That would be a significant detail as well. So I think we set this up to be pretty nice. Did that work out okay? Did that give us pretty nice answers? I moved all that across. I got a negative 10x and a positive 16. Anybody get nice factors on that? By the way, will they always be perfectly factorable? Only if the benevolent dictator made the problem that made it come out pretty. You know, it normally doesn't, but it's x minus 2 and so if that's the case with x minus 2 and x minus 8, then my two values would be x equals 2 and x equals 8, right? Now, I showed you one version of that a second ago, but the reality is, could I plug in 2 right here? What would happen if I plugged in 2 right here? Well, in a sense, I would get what I'm looking for, but the easiest thing is to go back here. So I'm going to go back to the easy version. And so what's the first one if I let x be 2? It would be 2. So this is a nice little line. So I'm saying it would cross and they would both have a slope of 2. By the way, I'm going to write that down. Y prime was 2x minus 2, wasn't it? So what's the slope of this line right now? The slope of this line is 2. What's the slope of this curve at y equals 2 is 2. We got it. Okay, and then the other one, y minus 7, here's x minus 5. What fills the little hole for using the value x is 8? Would that one be easy to see? No, crazy steep things are often a little bit more difficult. Now, when you guys were working on, quote, the fast way, I told you guys could do the first part, but I told you to kind of hold off and not go too far on the fast way because there were some problems in there. I'm looking for my copy of that. Let's see what happens right here. So notice when you get to the back, I have a story where I said, let's sketch the line, find K such that the line tangent to the curve is so that this line is going to be tangent. So let's go through the process. If it's going to be tangent, what do we need then? What are the rules that make it a tangent? I don't want to write on my original here, so I'm going to use a sticky note for the moment. So, what is f prime of x? Two x minus k. Okay. What is the slope of this line? What did I just set up then, everybody? Why did I set it up that? Because the first rule for tangent says that the slope of both have to be the same. This was f prime, which is a slope. This is the slope of the line. By the way, yes, you could have taken its derivative, but why bother? It was so easy. So what else must be true is not only must they actually have the same slope, what else must be true? They have to intersect, don't they? So somehow y being 4x minus 9 must be the same as x squared, shouldn't have put a parentheses around that, minus kx. So I'm setting these equal. I'm making the line equal to the original function, but I did something on purpose right there because I had too many variables. I guess I could put the k there. Maybe that would be helpful to you. But what could I put in place of k? Could I come up to here and say that 4 minus 2x would be negative k? So what's k itself? If I replaced k itself with positive 2x minus 4, see now what I did is I made sure that they had the same slope, but what else did I find? Is I made sure they were set equal to each other. Now this particular problem, you don't have to find the full tangent, you just need to find k that made it true. Is this going to be an easy one? Let's see. I got to be careful because I got to take this all the way out here times this x, and then what else is there? There's a negative and a 4 and an x. So I think that's going to be a positive 4x. Anything nice happen there? I noticed that the 4x's could go away, couldn't they? And I have negative 9 is negative x squared, right? So what does that make x? Careful. So if x squared is 3, x is plus or minus 3, and most calculus students smile and they put their hands up in the air and say, yay, I finished. And then their teacher gets mad at them because it said, don't find x, find k. Oh. But what did we just find out right up here was that k was 2x minus 4. So what are the two values of k that would actually make this thing work. If I plugged in the number 3, I would get k equals 2. And what happens if I plug in the number negative 3? I got k equals negative 10. Now, here's the rest of the story. Could you graph this in Desmos and this in Desmos and see if they in fact did intersect and have matching stories? And then you could change the k value from 2 to negative 10. Keep in mind that's going to be then a plus 10x, and you should be able to do it. So I think that's as far as we're going today. Looking at the clock, I still have just about 5 minutes. It's not a whole lot of time, but I thought maybe you guys could do a couple of problems on, quote, the fast way. So we have a few problems dealing with this idea of tangent lines. So I didn't do number 15 with you. And down here, this actually doesn't ask you to do very much, but it says, can you find where those tangent lines would be horizontal? Which, by the way, what's the slope of a horizontal line? There you go, okay. The slope of a horizontal line would be 0. So this is a fancy way of saying, hey, take your derivative, set it equal to 0, go get it, okay? And so that's kind of where all of that stuff is going to end. And so I think I wanted to stop and give you guys a little bit of a chance